Okay. So, now let us get started on the next lecture, that is lecture 3. We will discuss a few basic issues here which we will keep in mind, again an extension of the introductory part. So, let us start now. Just to recollect what we had said, that in a modern embedded system we have processors, need not be one, several processors, and then we have memory, and then the IO devices, input output, the sensors, actuators, etc. These are typically analog, and then we might have also application specific hardware designed specific to an application, and these can be ASICs, FPGAs, etc. Let us not bother about this because not the focus of this course. The application specific hardware is used here for ensuring performance and consuming low power, and then we have different types of processors. For example, some might be signal processors, digital signal processors, some might be controllers, etc. There might be mechanical transducers, actuators. So, we will just keep this in mind, but we will not really discuss this in a detail, which would be possibly a discussion in an embedded system course. We will not discuss about this. So, this is the kind of block diagram we will keep in mind, that there is a processor and the operating system is running on this, and the user interface processes and the controller processes, these are applications running on the real time operating system. And then we have digital signal processors and some specialized processors which possibly have their separate code, and there might be some application specific integrated circuits, and then we might have memory specifically for these DSP processors. Both of these are accessing this dual ported RAM, and we might have a codec for signal conversion and compression. So, this is the kind of system that we keep in mind as we proceed. But let us answer one very basic question before we look into the details of an operating system. Said that the system is small, embedded system, for example, a small cell phone or a microwave oven or a toy or something. Now, does it make sense to have an operating system there? Can't we directly program on the hardware? Why do we need an operating system? No, user input can be handled by a program written on that. You can always write, just like you have done microprocessor programming. You can handle user inputs, right? Microprocessor programming, you did not use any operating system, isn't it?
You can add new application program.
No, one application will run. What do you mean by new application program?
So base application, OS is the base thing, it will talk to hardware.
Right.
So, if any new application is coming.
No, but you are developing it for one application, isn't it? An embedded application is a special purpose application.
But for mobile phones, you can add some new programs. The upgradation will be difficult.
Sorry?
If the hardware alone is used, the
Yes.
upgradation may be difficult.
Okay. See, what he says is that, see, if you, it might be difficult to really make it bug free and all those, he is saying. It might be difficult to upgrade. Okay, let us see that there are many reasons why we need an operating system. So, let us look at them one by one. See, one is, we said that these systems have multiple tasks. So, we need to support multitasking, and we need to have some scheduler for this, and then we have issues of resource sharing and synchronization. So, if you want to implement all this as application program, you want to rewrite that, you are unnecessarily incurring additional cost which you could have just got these features by using an standard operating system with very little cost. Similarly, the timing aspects. How do you support timing aspects if you are writing your own program without an operating system? How do you ensure that it will run? And memory management, because these are basic functions in an operating system, and any application you write, it has to do memory management, isn't it? Because data it has to read, store. And what about file systems? How do you keep track of permanent data and read them? Need a file system. Networking, because as we are saying that all these devices are now being networked. How do you support network? Would you like write your code for the network protocols and handling the packet transmission? What about graphics displays? How will you do that without an operating system? Suppose you want to interface with different IO devices, will you write your own IO driver? That will be very expensive. Then buffering and scheduling the IO operations. What about providing security and doing power management? So, all these are features of any operating system, real time operating system, and if you are thinking of writing an application without using an operating system, it will become extremely large, development time will be too much, cost will be too much, and the product will not run, right. So, for every non-trivial embedded device, we need an operating system. Is this point clear? There are many reasons why you need an operating system, because these are basically multitasking, and we need to have proper schedulers for this. Resource sharing between tasks is required, as you will see that some results are produced by something, used later by another task, or maybe they just work together to produce some results. Memory management, file system, networking, graphics displays, supporting IO devices, security, power management, all these are provided by operating system. If you are thinking of not using an operating system, you will be unnecessarily incurring additional cost, time, right. Okay, let us proceed further. Just consider a cell phone operating system. This is one topic we will discuss later, the kind of operating systems that are being used in cell phone, commercial phones. The code is over 5 million lines of code, thus the operating system that is being used. Now, suppose a cell phone company says that, see, we want to reduce cost, let us assume hypothetically, because when you buy a commercial operating system and per product you will have to pay license fee. Now, the license fee may be typically small, maybe just a few tens of rupees, or maybe just a fraction of $1 per device, per cell phone. Now, if you do not use the operating system and say that, see, our programmers will write the basic features necessary to support that. Now, just see how much time they will take to write that 5 million lines of code to make that cell phone operate satisfactorily. And also the fees are not very high. Per device, the license fee that is paid is just few tens of rupees, and also there are free operating systems. But what we need to keep in mind here is that this kind of operating system, they do occupy some space, they have overhead. So, if you are thinking of extremely simple devices, like let us say a air conditioner, where it just samples the temperature and either switches on or off, samples temperature, switches on off, that is simple activity, then we do not need a operating system there. The event is just one temperature being sensed and then switching it on and off, that a simple program can do. But the kind of devices that are appearing now, becoming more and more complex, and most of these devices will see use operating systems. But before we actually start our discussion on the operating systems etc., let us look at these basic issues, that what kind of processors are used, what kind of operating systems are used, what kind of programming languages are used. We will examine some market survey that appeared in the Embedded Systems Design magazine. Now, let us look at the results. See, the processors that are being used in these embedded designs, vast majority is 32-bit, but for lower end application we still have 8-bit, 4-bit and 16-bit applications, and for some applications even 64-bit processors are being used. But maybe in future, as the embedded systems become more and more complex, maybe we need more powerful processors and powerful resolution, right, data resolution, data size, might need a 64-bit processor. The kind of processors that we are talking of in this kind of applications, a large chunk of the processors based on the ARM processor, PowerPC, MIPS, Xscale, which is again a type of ARM processor, but we will see that a vast majority in cell phone and all those are ARM processors, which is again based on the MIPS design. I hope in your architecture course, you had the architecture course, isn't it? So, in the architecture course, the MIPS, the design of this is or the arrangement of this is that they do not really manufacture MIPS processors, they just license it to different vendors. For example, Sony Corporation might be using MIPS processors, Toshiba might be using. Okay, let us proceed. Now, let us see, as far as the sales volume is concerned, the ARM processor has the maximum market share, as we are saying that many of these mobile phones actually based on ARM processors. But what about the number of processors used? We have majority one processor system, but we do have 2 processor, 3 to 5 processor and more than 5 processor system. So, in our discussion later, we will keep in mind about multiple processors being used in an application, and that trend is possibly becoming more and more number of processors, more and more number of threads per processor. That is the trend. Now, let us look another basic issue, that if you are developing an application, how do you select the processor? Kind of operating system it supports, because all operating systems do not run on all processors. Kind of compilers, debugging tool, applications you need, the price, performance, power it consumes, because for this kind of applications the battery life is important. Millions of instructions processed per watt, is there a cooling facility, availability, whether you can get in sufficient number and time, those are issues, not spend time on this. But what about operating systems that are being used? See, a large majority, more than 50%, they have used commercial operating systems, and the simpler ones, about 30%, slightly less than 30%, they use no operating system, because very simple systems, internally developed operating system for simpler applications, and then open source operating system. These come without cost, right, but this is a growing segment actually. But let us see what are the problems with open source operating system, because as we proceed we will also discuss different types of open source operating systems. So, let us look at one basic idea which we will remember throughout the course. See, one thing is that goes in favor of open source operating system is that devices are extremely cost sensitive, because the total cost is, let us say, 500 rupees, and out of that if you pay some 20 rupees for operating system license, then another competitor might actually underprice you by not using an by using an open source operating system. So, for commercial operating system paying a license fee, you will just try to use open source and reduce the cost, very competitive market. So, that is one thing going in favor of open source operating systems, and people actually exploring to use open source operating system. Now, but for satisfactory performance, this open source operating system need to be fine tuned. You can't just get it and use it, right. You have the code, source code is available, these are open, and you need to fine tune, but that is not a problem, could have also used without fine tuning. But let us see the problems. See, cost is one thing, you could reduce cost, but let us see the problems, why there are majority still going with commercial licensed operating systems. See, one thing is that even though we got the operating system free, but these free operating systems, the open source operating systems, many of the new devices, they do not get drivers, device drivers. So, possibly you will have to write device drivers, which will increase the labor cost, whereas the licensed ones, as soon as a new hardware becomes available, IO device, a new device becomes available, they immediately develop the device driver and support it. And there are other problems also. One problem, just see here, that as part of the open source license, it is not that you will just get it, change it and use it. You will have to sign a license which says that whatever you develop based on this operating system, you will also make it in the public domain, you will make it open. So, very few developers, product developers will be agreeing to put their code on the open platform because of business reasons. And for other plug-in software still need licenses, they are not part of this open source, for example, media player, encryption, encoders, decoders. So, possibly these two, that you do not have many device driver support or recent device driver support, and also you would have to abide by the open source license. These may be deterrents for using a open source in a commercial product. But if you are using the operating system as it is without much difficulty, I mean without much tailoring or rewriting, then you can, it makes sense. But again, to get programmers who understand that code and write it and support, if you have a problem there in the operating system, how do you, who will support it, right. So, those are the issues. Okay, let us proceed further. So, out of the commercial operating systems, let us see the market statistics, actually slightly older statistics, 2006, published in literature. The Microsoft has a large share here, Microsoft embedded, and then we have Wind River system. They have several operating systems under the Wind River, which are also very popular, and then we have Symbian, Green Hills, Palm OS. These are some of the terms, names we will use as we proceed in this course, and of course, there are the free operating system, and these are the small players in the commercial operating system area. We will look at it in more this thing detail, the typical products that are there, the popular products, not typical, the popular products under from these commercial organizations and their features, how they compare for using in a typical application. We will look at those features later. Now, what about the programming language? See here, large majority is with C language. It is not really C, but a subset of C, because they do not use pointers, dynamic memory allocation. These features are not used in a typical embedded design, because they are sources of error. So, the standards here is they have defined a new standard for embedded system programming, where they define the subset of C that is being used. C++ is also quite popular.
So what is that subset of C called?
I think it is called a standard. I will just give you the exact organization which has produced the standard, right, for embedded programming. It's the syntax and the semantics, a subset of the C has been specified, which are being used by organizations across. I will give you the organization and the standards name. Misra standard, yes, but Misra, is it the automobile, but what about the general embedded? We will just discuss that later. I do not recollect now the name of the standard and who has made the standard. So, C# is also being used. Java, of course, because of its different technologies that are available with Java, especially in the mobile environment, right, mobile phone environment. Assembly languages are also used significantly, and other programming languages. So, as we proceed, we will hear less about embedded systems. So, this is possibly one of the final slides that we are hearing about embedded systems. So, in the future, what are the trends? Because this we will also have to keep in mind as we discuss about the software issues. More and more they are using multi-core processors, where in the same semiconductor packaging, the same processor will have multiple cores, and the challenge that it poses for our discussion in the subsequent lectures is that the operating systems and tools, how do they make effectively they use the multiple cores available, and support for wireless and mobile internet. So, how would one support internet while on move? Power minimization. So, these are some of the issues that will become more and more prominent in the coming years. Now, let us start. Possibly we will not discuss about embedded systems and the basic issues. Let us look at the types of real time systems that we will be discussing. One thing that we have so far said is that every task here in a real time system has some, the real time tasks. I am not saying every task in the system, but the real time tasks are those which have deadlines or some form of timing constraints associated with them. So, based on this we can classify the tasks as hard real time, soft real time, or firm real time, very basic issue. And later if you say that I have done a real time systems course, somebody might, the first question asks you is that what is a hard real time system? How is it different from a firm real time system, or how is it different from a soft real time system? Give examples of this, right. These are basic questions in any, if after having done this course anybody can ask you this question. So, let us look at it. In a hard real time task, even if a deadline is not met, just one deadline is not met, we will say that the system is failed. And another thing that we need to remember is that the deadlines that we are talking of for hard real time tasks are of the order of micro to milliseconds. never in seconds or minutes. All these hard real time systems, that the examples we had seen, several of them, starting from robots to a chemical plant to onboard computer, all these, the deadlines are of the order of a few micro or maybe few milliseconds, not more than that. And many of these hard real time systems are safety critical. We have seen several examples, but these two are important points, that that is the basis on which we will distinguish that if one failure has occurred, what is our opinion of the system? Is it failed or can it still continue to work? And then what is the kind of the deadline we are talking of? A firm real time system is one where even if sometimes a deadline is missed occasionally, the system does not fail, but only thing that will happen is that the result will be rejected. The result produced after the deadline will be rejected. So, we can draw this kind of diagram and say that, see, as long as the result is produced within time d, we have the result will be used. Utility is 100%, I mean the result will be useful to us or to the system. But after d, if the result is produced, the utility of the result is 0, will be thrown, right, will be discarded, but the system will not fail. But if it fails once in a while, it is all right, but if it just every task fails, then we will have to say that it is failed. What about examples of a firm real time system? Typically, all video conferencing and multimedia type of applications are firm real time system. Suppose you are in a video conferencing mode and then a frame is missed or a frame could not be processed, you would hardly notice it, because there are 50 or 60 frames being repeated every minute. I mean, the number of frames repeated depends on the quality of your video conferencing system. Quality is poor, might be some 20 or 30 frames being repeated. High quality video conferencing, you will have many more frames that are repeated per minute. So, one or two frames getting missed occasionally, the user will hardly notice that, and as soon as a frame arrives late or for some reason could not be processed in time, you do not show that later. If you show that later, then you will see a glitch or you will see a problem in the picture, it just discarded. The frame, a frame which could not be processed in time will be discarded and the users will hardly notice that, right. So, the result which could not be produced within the deadline, right, before the next frame could be processed, or if the repetition rate is something, it could not be processed within that repetition rate, then it is simply discarded, not displayed, right. So, that is an example. We can have telemetry applications. If a new data becomes available, do not need the old data, you might discard it. Before the old data comes, the new data which has come and processed, will discard the new data without any much difficulty, because after all just measuring something for weather or something. Then satellite based surveillance application, we are surveilling, doing a surveillance, no, that we are getting signals and processing and seeing whether there is a movement of army or what is the crop, that kind of surveillance. So, if a data could not be transmitted in time, we have the new data for surveillance applications, we will use the new data, discard the old data. So, these are some of the examples of a firm real time application. But what about soft real time? A soft real time application, if a deadline is missed, the system does not fail, just like a firm real time system, but the difference is that the result still is used, even after a deadline has passed, the result is not thrown, it still has diminishing utility value. So, the utility of the result decreases with the time after the deadline. Is that okay? The difference between a hard real time, a firm real time and a soft real time. But what are the examples of soft real time? Let us look at a railway reservation system. Let us say you are standing in the counter for a railway reservation system, and the clerk there took your application for some train journey and just keyed in the detail, and the system does not respond, you are just keeping on waiting. See, if it comes, let us say within 30 seconds or 20 seconds, you say that the system is very fast, and you come with the ticket very happy. Now, let us say it delayed 3 minutes, he has given the data, still you have to wait 3 minutes, and then finally it printed. So, we will say okay, fine, it was slightly response time is not good. Now, what if keyed in the data and even after half an hour still nothing has come out? What will you do? You will just walk out, you lose patience that possibly it is not working, and you will come out. So, as long as it is in the human response time, see, if it is within 20 seconds or something, you will not notice 20 seconds, say that it has come instantly, and you will come happy saying that response is very fast. As soon as I gave the request, immediately ticket is printed and delivered. Similarly, in the case of web browsing, you just clicked on a link, and then if it what appeared to you instantly, see, what appeared to instantly is not really instantly, it is not in microsecond or millisecond, several seconds. If it comes in several seconds, you say that, see, it is good, it has come very fast, but let us say you have to wait for 3-4 minutes, so that system is slow or that site has some problem. Now, after 10 minutes it does not come, so you say that, see, there is problem, it is not usable. So, here just see that if it has come within some 20 second or 30 second, say that the system is working very good, and then you are saying that the response time has decreased. The system is not as responsive, but you are not saying that the system has failed. So, in that sense, every application that you use is actually soft real time. I mean, every application in your desktop or in many of the everyday life you use are soft real time. For example, you are doing a word processing, and sometimes you make a change on the word processor, immediately reflected, and sometimes you just made a change and it is taking time, possibly it is doing something internally, right, saving some file or doing some logging or some activity, takes little bit of time. You do not say that the system has crashed or something, you wait, right, and if you are to wait very frequently and for longer duration, say that the response time of the system for some reason is not good, right. So, most of the tasks that we are familiar are soft real time. The firm real time and the hard real time are the one that we are going to discuss in this course. Soft real time, occasionally we will talk of that in addition to hard real time and firm real time, some soft real time tasks also systems might have to support, right, real time systems, but majority of the tasks that we will talk of are either hard real time or firm real time. Now, is there any task which will be non real time? What do you think? See, we talked of a hard real time, a soft real time, firm real time, but can a task be non real time? Yes, anybody would like to answer? Can a task be non real time?
Like a complex simulation, scientific calculations, we are not concerned about the time, we just concerned about the result.
Okay. Okay, he says about a simulation application, it runs days together, but sometime it might, so you do not know that. So, maybe you will come tomorrow and check, not running, come next day and so on. Any other application you have in mind? non-real time application, non-real time task, let us say.
Decryption and then tracking a message, decrypted message.
Okay.
Cryptography takes days together. And if it is, even if it is 2 days, then we say it's okay.
Okay. Okay. Or let us say in the salary section, they gave a printout for salary, right. They gave the printout, takes time, went for a tea and came back. So, if it has completed, okay, fine, not completed, it is going on, they will check again. So, time is not a matter there as long as it is going on printing, right. So, one thing that distinguishes between the soft real time and the non-real time, okay, can you identify that? See, soft real time also, their time is of very little concern, is not it? So, what is that distinguishes? See, here you went for a coffee break and came and found whether it is printing or not printing, and then you again checked later whether it has completed. But in a soft real time also, you just waited with patience, checked whether it is printing the ticket or no, right. So, what exactly is the difference between a soft real time and a non-real time task?
In a soft real time, we are doing some in a non-real time system, we can do some other task while our task is being completed. But in a soft real time system, we are stuck in that task while the task is being done.
Okay. Okay. In other words, what he says is that in a soft real time, the time scale that we are talking of is couple of minutes, whereas in a non-real time task, we are talking of time in hours, right. So, the dimension of the time is possibly the difference, because if the payroll is supposed to have been printed within an hour and is still going on, so you say that it has failed, it is printing possibly something junk, you go and check, right. So, the scale of the time is actually the difference between a soft real time and a non-real time task.
Sir?
Yes.
Sir, can we talk about the utility of the output that we get? Like we are saying that in a soft real time system, the utility is supposed to decrease of the
Yes.
output that we get.
Yes.
But for a non-real time task, like if the printout comes after 2 hours, but still the utility of the printout of the output is not hampered, like it is not diminishing.
No, see, it is taken your time, right. Utility of the result has diminished, just like in a ticket counter, railway reservation counter, you got your ticket, but after let us say 2 minutes. So, the utility is less, it is not, no, you had to wait, you are not happy, right. So, the utility of the result is less. If it came instantly, you came back happy, saying that it is responsive, otherwise you are saying it is in a degraded performance. Same thing here, that if it appeared in let us say 15-minute printed and you are expecting an hour, say that okay, it has printed very fast, and after 1 hour if you come and check it is still printing, you will again say that somehow it is very slow, let me come after some time, right. It is a degraded performance. Same thing, but the scale of the time one that actually distinguishes these two. Or maybe let us say email, in a good time it just reaches instantly, right, maybe in few seconds, but let us say it can also take 5 minutes or it can take half an hour, but if it does not reach by a day or so, you say that see it is not going to reach. So, the time scale that you are prepared to wait for that task, that is actually the one we can say distinguishes between a soft real time and a firm real time, and say that email is not a soft real time task, it need not complete in a minute or couple of minutes, it can take several hours, right. So, this is the scale of the time is the one which really distinguishes between these two, right. Okay, let us proceed further. So, any interactive application you can say is a soft real time task. See, printing is actually not an interactive task, you just pressed a switch and then we are waiting for the result. Similarly, email, but if you are interacting the computer, entering data, looking at the response, entering again, so then those are usually soft real time. Now, we can also say that a task, in addition to being a hard, firm or soft real time, can also say that whether they are periodic, sporadic or aperiodic. This is another dimension of classifying tasks. We will use these terms very frequently as we proceed. The periodic task is one which repeats after some fixed time interval, keeps on occurring based on some time. Just look at the term time. So, somehow some clock is there giving a time interrupt and the task is rising, right. For example, you are trying to sample temperature every 100 millisecond. So, there will be a clock which is giving an interrupt after 100 millisecond, and based on the interrupt the task of sampling the time is arising. Is that okay? There is a concept, there has to be a clock in every periodic task which as soon as it gives interrupt at periodic times, then the task is getting fired or it is arising. Okay. Now, a sporadic task on the other hand occurs at random instants. For example, a fire condition, or let us say temperature becoming very high. Suppose we just monitoring the temperature, the sensor will monitor temperature and it will send a signal as soon as it is more than some, instead of sampling it periodically, just sends a signal once it becomes exceeds some value, or let us say a fire condition or a smoke condition being sensed. So, these are sporadic tasks, you can't say when they will occur, at random instants they may occur, right. Now, there is another task, another type of task, we will also use this term aperiodic. So, here these are also sporadic tasks in the sense that they occur at random instants, but the difference between a sporadic and aperiodic as we will use is that a aperiodic task we can have several of them arising even at the same time. For example, different users are there and they are giving inputs to the system. So, they might give input very random time, or they might just give at the same time all inputs has come, or let us say we are monitoring fire condition at different places, and let us say fire can occur at different places at the same time and different signals will come. So, that may be a sporadic, right. So, aperiodic. So, sporadic and aperiodic are similar terms with a small difference. One, there is a minimum difference from one event to another event, whereas in a aperiodic the events can occur any time and even at the same time. But just to summarize this classification on real time task, a periodic task is driven by clock. The clock event is the one which is important for a periodic task, whereas for sporadic and aperiodic the events are not driven by any clock, can occur any time. Okay. Now, let us look at some basic issues in task scheduling, because we said that this is one issue which will be there in every operating system that we talk of, and this is the primary means by which the deadline will be ensured. So, do you have a class after this? Okay. So, I think we will just take up this topic in the next class about task scheduling, right. So, we will just stop here. Okay, thank you.